So today is a lesson on chirality. I chose this because I saw this question, this entry-level question on the Cambridge Chemistry Challenge, and I thought it would relate quite nicely to it, be a nice opener. So I'm gonna start off with my thought process when I first saw this question. They're usually one-word answers that you're supposed to sort of deduce from the image. There's also rules. Basically, you can do anything you want to try to get the answer, except for Googling for the answer itself. So when I first looked at this image, you can see a hand sort of reflected in a mirror holding chewing gum that is spearmint flavored. But I did notice that this mirror was quite weird, in that if it was a mirror, if it was reflecting sort of like that, then the thumb should instead be up here where the pinky is, and the ring being on the fourth finger should instead be on this finger, so it does look a bit weird. So instead it does quite look like the hand is not reflected by a mirror and instead is reflected across a plane like this. And this instantly made me think of chirality. One thing about chiral molecules is that they are the same, they are made of the same atoms in the same groups, but they are non-superimposable images of themselves, and what that means is that when they're reflected in a mirror, they will never quite look the same. You'll often find these in nature, and an example of this are actually your hands. So if you sort of look at it in this way, it does sort of look like this is your left hand and this is your right hand. And one thing about chiral molecules is that no matter how you try to place them on top of each other, their groups will never quite align themselves up. So if you take the example of your own hands, you can make your third fingers match, but you can never quite make your other fingers do. So your second finger would align with your fourth, and the thumb on your right hand would align with your pinky, sort of like this image. And this actually doesn't quite look like it's reflected across the plane like this, because when looking at the writing, flavor is sort of reflected that way, and I suppose the answer would be to fill in the blanks that these question marks are posing. So it would be replacing spearmint. So that made me think that we were trying to find the chiral molecule of spearmint, and if we actually do Google spearmint chiral, I think we do get carvone. And now carvone itself is the group used to describe spearmint and its chiral molecule, caraway. These two molecules, they have the same, they're sort of arranged in a similar way, sort of reflected down the middle once more. Their groups are the same, so they're called enantiomers of themselves, carvone being what is used to describe both of them. So we here have spearmint and we here have caraway, so from this I assumed that the answer would be caraway. So I think if we do type in caraway, we get the correct answer. Yep. And here it does say this atom makes a chiral, and what this actually means to say is that what defines a chiral molecule is when it has one carbon atom surrounded by 4 different atoms or groups of molecules. So in this case, if we take caraway as an example, it would have one group going down here, one group to the left, one group to the right, and one hydrogen behind it, because this carbon only has 3 single bonds, so it must have a hydrogen behind it. This gives it its tetrahedral arrangement, and also makes it a chiral molecule because these 4 groups are all different. Another thing about chiral molecules is that they're often very different to our bodily senses, as in receptors in our nose, smell, flavor, or the cones and rods in our eyes respond differently to the same enantiomers of the same chiral. Now, how do we actually define what type of chiral it is? If we take the